one of the things that's useful is using the numerical value of the reaction quotient to two things, to tell you whether a system is at equilibrium, or to tell you which direction the reaction will favor, either directly from delta G or indirectly from information in the problem. So let's start with actually calculating the value of a reaction quotient. This is the same exact procedure that you use to measure the value of the equilibrium constant. To determine the value of an equilibrium constant, all you need to know is all of the concentrations at equilibrium. First step is to use our previous skill, write the correct equilibrium statement. Again, this is one of those foundational ones. We do get that wrong, everything else will be off. So, write the equilibrium statement for this. Q will be equal, reaction quotient will be equal to products over reactants, Cl4 minus 2 raised to the power of 1 divided by the concentration of the cobalt times the concentration of the chloride ion raised to the 4th power. This will allow us to calculate a value for Q given concentrations. What are the concentrations? Well, the problem supplies us with some. Right? What are the concentrations under these cases? Under standard state conditions, these all equal 1 molar, and this value of Q drops to 1 and falls out of our Gibbs-related equations. But most of the time, we're not working under standard state conditions. We're working on non-standard state conditions. So what are the values for these? Well, in the problem, we have values shown here. And so all we have to do is plug those into our calculation. Q will equal concentration of the cobalt tetrachloride is 1 times 10 to the minus 5th molar. Concentration of the cobalt plus 2, 2.0 times 10 to the minus 2 molar. The chlorine is 4.0 molar to the 4th power to give us a value for Q. Now, the units here look like they are 1 over molarity when you multiply it out, but in reality we're not actually using molarity, we're using something called activity, which is dimensionless. And you'll learn a lot more about that in analytical class. Times 10 to the minus 6th. So under these conditions, the reaction quotient is equal to 2 times 10 to the minus 6th. Again, very straightforward. If this had been asking you about equilibrium, the question would read very similarly. Here are the concentrations. What is the equilibrium constant under these conditions? And this would be the value.